we are looking at a sine function. Okay, the function itself given to you is y equals to sine x plus 1, and it says that it meets the x-axis at the point A. Okay, we want to find out what is this coordinate over here. And since it meets the x-axis, that means your y is equals to 0. So in part I, we let y equals to 0 to help us to find out what is the coordinates of A. So in other words, we're solving a trigonometric function. Okay. So because it's sine x plus 1 equals to 0, you may want to take a look at your quadrants, but usually when it comes to 0 itself, I don't rely on the quadrant. Okay, so what I will rely on is our basic sine graph. Okay, so how do we make use of our sine graph itself? When it is equals to 0, that means your y is equals to 0. We're looking at these 3 points. Okay, and we need to understand that for our very basic sine graph, period is 2 pi. We are looking at radian mode. Okay, so when it comes to your area and all that, we are always using radian mode. Okay, we don't use degree mode because it is not sensible for us to be using degree to calculate area lah. Okay, so we use radian mode. So 2 pi, pi, and 0 over here. Okay, so these are the 3 important points that will result in y to be equals to 0. These 3 important points, okay, is for x plus 1 because the angle that we're talking about is x plus 1. So x plus 1 equals to 0 or pi or 2 pi. Okay, hence x equals to negative 1 or pi minus 1 or pi minus 1. Okay, but then with reference to the diagram, A is just 1 point. It is not possible for it to be all 3. Okay, we need to make sense of the values that we have gotten, okay, and reject accordingly. Okay, A is clearly on the right side of the x-axis. Okay, on the positive side, since it is on the right of 0, that means x cannot be equals to negative 1. Okay, and since this is the first encounter on the x-axis itself, that means that 2 pi minus 1 is also not possible. Okay, which explains why the x coordinate of A will be pi minus 1. Okay. Then we proceed to find the area of the shaded region, which is what part 2 asks for. So to do that, we will integrate from 0 all the way to A. So A's x coordinate is pi minus 1, so integrating from 0 to pi minus 1. And we integrate the function sine x plus 1. Okay, with respect to x. Okay, and integrating sine will give us negative cosine. We divide by the coefficient of x, which is 1, bounded by the value 0 to pi minus 1. Okay, then we substitute in the values. So negative cosine pi minus away negative cosine 1. Using your radian mode in your calculator, we will get a next question. Okay, just an additional question that I want to include into our understanding of definite integrals. Okay. This question is not found in the textbook, so let me just write it down. About how the function looks like. It just tells you that the integral from negative 1 to 3 for that function gives us the value of m. Okay? And they want you to evaluate or to express in terms of m. Maybe express in terms of m. Okay? All these three integrals. So let's look at the first one. The first one is to integrate from 3 to 3. Okay, so if you try to imagine and link it to the area under the curve, right? Okay, 3 to 3, whatever curve it looks like, okay, at a certain point itself, if it is between 3 and then again at the same thing, okay, so what is the area going to be? There will not be any area, right? Okay, because area will definitely need more space in order to constitute an area. Okay, so therefore, integrating from the same values, okay, for the lower and upper boundary, the value will be equal to 0. Okay, so that we need to know. And then in part 2, okay, integrating from negative 1 to 3, 4 times of fx. We know how integration works, where we can take out the constant. Okay, and then this value we are already given that it is equals to m, so therefore it will be 4m. Okay. Okay, the more important one that I want to cover is part 3, whereby we are given 3 to negative 1. Maybe let's start off with something easier. Let's drop the pi over 2. Okay. We're given negative 1 to 3. So what we need to do about this? Okay. So what we can do is that we can apply our negative sign in order to switch the boundaries. Okay. So integrating from 3 to negative 1 is equals to integrating from negative 1 to 3. I'll explain in a moment. Okay, then after that we'll get negative n. Okay. Boundaries, we apply a negative sign over here. Okay, the reason is because, okay, we understand that if I want to integrate a certain function, it gives us another function. Okay, so we have this capital letter F to represent the new function. Okay, and then we have this plus C. Correct? Okay, so that's how we do our integration, right? Then, if let's say I'm looking for a definite integral, we're integrating from 2 to 5. Okay, what we will usually do is that we will integrate our fx to get a new function, capital letter fx first. Okay, and then we substitute in the value of 5, followed by minusing, okay, substituting the value of 2. Agree? That is what we do in our definite integrals. Okay? Now what if I switch it around? Instead of 2 to 5, it becomes 5 to 2. Okay? The same concept will still apply, whereby when I integrate the small f, I'm going to get big F, and I substitute in the upper boundary first, followed by minusing the lower boundary. Agree? So what is the observation that we make from this one and this one? Okay? When it is 2 to 5, we have 5 minus 2. When it is 5 to 2, it is 2 minus 5. It is the reverse, and we know that F5 minus F2 is equals to negative of F2 minus F5. Because algebraically, we know that upon expansion, I'm going to get negative F2 plus F5, which is the same thing as positive F5 minus F2. Okay, so that's why when I switch the boundaries itself, I can apply the negative sign to do the switch. Okay, so this may be some of the questions that you may encounter. Okay, and we need to be clear about how the boundaries can be swapped, okay, and the impact of it. Okay, where we need to apply this negative sign. Okay, any questions? All right. Then let's take a look at a new question. Question 3, part I. We want to sketch the graph of y equals to x squared. I hope that you know how y equals to x squared looks like. Okay, so it is your quadratic curve. Coefficient of x squared is positive, so happy face. And it must pass through the origin and symmetrical about the y-axis. Okay, but because the question mentioned that it is supposed to be a sketch from negative 2 to 2, so we need to intentionally put in negative 2 to 2. Okay, and also what is the corresponding y coordinate? That will be equals to 4. Okay, so this will then constitute a complete sketch for part I. Observing the shape of the graph and given that the integral from 0 to negative 1 of x squared is equals to m, in other words, okay, the area under the graph is for negative 1 to 0, which is this one, okay, sorry, 0 to negative 1. Okay. It's 0 to negative 1. Integrating from 0 to negative 1, it is equals to m, okay, which is somewhat over here, just that this one is 0 to negative 1 and not negative 1 to 0, okay. So this area will be negative 1 to 0 x squared dx. It will be equals to negative m. Okay, why? Because for this one here, it is from 0 to negative 1. Lower boundary should actually be lower, smaller in value. If it is 0 to negative m, the other way round, and it is given to be m, that means that if I need to switch the boundaries, I need to apply my negative sign, okay, to get negative m, right? Okay. So in part A, to find the integral in terms of m for 0 to 1 itself, which will be this area, and knowing that our quadratic curves are actually symmetrical, that will mean that it will be equals to negative m, okay, since this area must be the same as this area. And then in part B, to find the integral from negative 1 to 1 for x squared, that will mean that it's negative 1 here and 1 over here. Okay, it is the sum of these two areas. So each area is negative m. It will be negative m plus negative m. So we get negative 2m. Okay. From this result, we can make another observation. Okay, so from part B, we get negative m plus negative m because we know that from negative 1 to 1, it will be this range and the area will be symmetrical, so negative m, we add them up. Okay, but what we can also observe is that for the integral from negative 1 to 1, we are actually breaking up into two separate integrals, one from negative 1 to 0, the other one from 0 to 1 itself. Okay, so our understanding about integrals is that it is continuous. Okay, so I can break up the boundaries into two separate parts. Okay, so negative 1 to 0, then 0 to 1 is continuous in this manner. Okay, because our area itself is continuous. Okay, so there might be times whereby we need to actually see it in two separate continuous intervals. Okay, from negative 1 to 0 and 0 to 1. It can also be others, so I can in fact have maybe negative 1 to negative half, and negative half of 1 as well. Okay, so long as this number here and this number here are equal, okay, adding it up together, it will be the same as negative 1 to 1. Okay. Right? The thinking about our integrals being broken up in this manner will be very helpful when later on we look at questions involving regions below the x-axis, okay, where we have to separate out into two separate integrals. Okay? Okay, so now that we have looked at the area under the curve for above the x-axis, we will next look at area under the curve, okay, area of the curve that is below the x-axis itself. In other words, okay, when your curve lies below the x-axis, how then do we find out the area of, let's say, this one? Okay. So because it is below the x-axis, it will be negative value if you were to integrate from a to b for the function that we're given. Okay? If you integrate as per normal, whatever function that you're given, it will come out to be negative. But because you're looking for area values ought to be positive. So therefore, we will have to include a negative sign to counter the negative value that we will eventually get. Okay? So the definite integral itself will be negative, but if it is below the x-axis, we must put in the negative sign. Okay, let's look at this question. We are given a function with the equation y equals to 1 minus 1 over x squared. We want to find the area bounded by the curve, okay, the x-axis, as well as the line x equals to 0.5 for the first part, okay, and for the second part bounded by x equals to 5. Okay, so what this means for part I is that we're looking at boundaries of the curve, the x-axis, and also the line x equals to 0.5. So we're looking for this area here. On the other hand, if you're looking at the area bounded by the curve, the x-axis, as well as the line x equals to 5, we are looking at this area. Okay. So in part I, the area, because it is below the x-axis, we have to apply a negative to the integral. Okay. And we are integrating from x equals to 0.5 to x equals to 1. So we're looking at the curve towards the x-axis, okay? And since it's below the x-axis, we have to apply the negative sign. Yeah. Then we proceed with integrating. 1 will give us x. Integrating 1 over x squared, that will give us negative x to the power negative 1 or negative 1. Okay, so we leave the negative sign outside of our brackets. Okay, then we simplify it. Substituting x equals to 1, we get the value of 2. Substituting 0.5, here we get 2.5. Right? But of course, you can press into your calculator directly, okay, in its full form. You you will eventually get 0.5 units squared. Okay, make sure you remember to write down your units. So if you didn't have the negative sign itself, okay, eventually your answer will be negative 0.5. So the entire purpose of the negative sign is really to make the area positive. That's all. Okay. And then part 2 is something that we have already been doing. So we are integrating from 1 to 5 for the same function. Make it slightly more complicated by looking at another question. Okay, so in your textbook question, they only gave you these words. Okay, we want to find the sum of the areas bounded by the x-axis and the curve. Okay, they did not put in this inequality, so this inequality is something that I added in. Okay, so that the question is solvable. Alright. Now, how do we go about solving it? Okay, we draw a graph to actually illustrate the question in order to understand what we're supposed to find. Because if you had not drawn the graph, okay, very likely you will miss out on the negative area, meaning to say the area that is below the x-axis. And if you forget to address that by putting your negative sign, the sum of your area, okay, will not be the actual area that you need to find. Okay, because below part will be negative, it will counter or minus away the positive areas. Right? So drawing the graph is necessary. Now in this case we have a cubic graph because this extends out to be cubic, x times x times x. So you need to know the shape of your cubic graph. Okay, in this case the roots of this graph is x equals to 0, x equals to 2, and then x equals to 3. Right? So we know that our graph will have to look something like that. A little bit like a sine graph, but it's not sine. Okay, something like that. Right? So this is your cubic graph. Alright, we learned it last year in your E-maths, huh? Okay, your chapter 5, I think. Okay, so the roots will tell us, okay, and then after it must go upwards first because it is a positive x cube. Right? Then, okay, why I introduce this boundary? It is because if I don't have this boundary, okay, the area is bounded by the x-axis and the curve. Strictly speaking, it goes on infinitely because your line here goes on infinitely. So I added this in. So that what we're trying to find out is this one and this one. Okay, so if you don't have the diagram, likely you will think about integrating from 0 to 3, okay, for whatever that you have, and then figure out the area. And when you do this, okay, the area is not going to be the sum of these two, because this will be negative. It will counter parts of the area over here. Right? So in order to find out the area, we have to integrate separately. In this case, integrating from 0 to 2 first. Okay, and then we have to add in this below x-axis part, and because it is below x-axis, it will be a minus instead of a plus. And we are integrating from 2 to 3. Okay, so this minus is because I'm just writing it in short. Okay, so the integral is below x-axis. That's why I must have the minus sign. Then now we proceed with integrating. Okay, x times x minus 2 times x minus 3 cannot be directly integrated. We need to expand it before we integrate. So you may want to do your expansion separately. So we are integrating your x cubed minus 5x squared plus 6x. Okay, okay, so the area troublesome, because if you want to attempt to calculate everything at one go using your calculator, you might get lost somewhere because it will be very long. So I would suggest that you press calculator in parts. So first one is to sub in x equals to 2, then you press your calculator, determine what is that value. In my case, I got 8 over 3. Okay, then we sub in x equals to 0. We observe that substituting x equals to 0, everything will be 0. So eventually you're minusing 0. Then in the second part, I sub in x equals to 2. Sorry, this one is 3. I sub in x equals to 3, and what I will get is 9 over 4. And then when I sub in x equals to 2, I'm going to get back 8 over 3. Okay, and therefore my answer will be 3 and 1 over 12. Above the x-axis, Okay, we have also covered area that's below the x-axis. Okay, now the next question is what if it is to the y-axis instead. Okay, so area of the region between the curve and y-axis. Area between the curve and the y-axis, it is as though we are just turning the graph around. And when we turn the graph around, okay, we are looking at y-axis as like our horizontal now, okay, and this must be y values. So your boundaries over here must be y coordinate values, unlike what we had, okay, whereby our boundaries are x-axis values, okay. And because we turn it around and our reference axis is our y-axis now, okay, whatever function that we are given, we must make x the subject so that it is in terms of y. Okay, and then we will be integrating with respect to y. Okay, so that is the challenge when it comes to figuring out the area, okay, to the y-axis. Okay, so we have to make x the subject. So let's do an example. Your function with y the subject and in terms of x. So in this case, we have y equals to 4 over x squared. Okay? And what we want to find is the area bounded by the curve and the y-axis and the lines of y equals to 1 and y equals to 4. Okay? Of course, if you want to actually solve it by keeping to the x-axis one, the x-axis idea, you can. Okay? So let me just show you how we can solve this without using the area to the y-axis. Okay, we know that. Okay, we know how to find out what is the area below the curve already, right? To the y-axis. So this entire area itself, okay, will be integrating for a certain number a to 2 4x squared dx. Right? But the thing is that I don't want this part. So eventually I must still minus away the rectangle. Okay? And then we still need to include this rectangle over here, which is 1 to 4, that's 3 units, and then this number of units. Okay, so plus another rectangle. Okay, so it is complicated if you want to actually solve it by making use of towards the x-axis. Okay, so that's challenging, right? Because we need to find out what is this value. Okay, so to avoid all those challenges, okay, in order to find out what is this area here, we integrate towards the y-axis, and the only inconvenience that we have is that we need to manipulate y equals to 4x squared and make x the subject. That means x squared equals to 4 over y, and x equals to plus minus the square root of 4 over y. Okay. And based on our search understanding, it will be 2 over square root 5. But then we cannot be integrating a function that is both positive or negative. So then what do we do? Okay, observing the context that we're given over here, okay, our x values are all positive, alright? So therefore, with the two options of positive and negative, we have to reject the negative because of the context of this situation. Okay, our x values are positive, so we need not deal with the negative x-axis. Okay, so the function that we look at will just be x equals to 2 over square root 5. Okay. The question has already been conveniently made such that you already know the boundaries of 1 to 4. Okay, so we are going to be integrating our 2 over square root 5. Okay, from 1 to 4 with respect to y. I want us to be careful that it is with respect to y. Very often, okay, you overlook this part and write dx instead. So in other words, we are integrating 2y to the power of negative half. To integrate this, we will have 2y, power plus 1 is half, divided by the power, and then from 1 to 4. Okay, since we are dividing by half, it means times 2, so we are having 4y power of half, 4 to 1. Then we do the substitution as per usual. We will have 8 minus 4. And that gives us 4 units squared. So definitely simpler than to actually break it down into so many parts to integrate. Okay. Alternative manner, okay, you will realize that try 11 doesn't allow us to do it with respect to x. Surface level. Okay, we want to find the area of the region P. This is the area. Okay, it feels no different from the questions that we were dealing with earlier, which is to integrate the curve, okay, from 1 to 2 ln x with respect to x. Right? But the problem is that, can we integrate ln? We cannot. Okay, so that's the problem. Right? In this question, we don't have the skills to integrate ln. So therefore, we need to push for a different way of thinking in order to figure out the area of region P. Okay, and in order to do that, we think of the alternative, which is to find out what is this value, okay, and then we see the rectangle here, okay, rectangle is easy, right? We have length and breadth, okay, then after that we minus away the area of this part here, which is to see the curve towards the y-axis, okay, then we will be able to get the region that we want. Okay, so that will be the strategy in solving this question. Okay, because we are limited by not knowing how to integrate log. Okay. So first we find out what is this value. That is when x is equals to 2. So y equals to ln 2, and therefore I get that this value is ln 2. Okay, the area of the rectangle will then be length times breadth, so ln 2 times 2. We leave it exact first, 2 ln 2. Okay. Then we figure out what is the area towards the y-axis. And since we need area towards the y-axis, our y equals to ln x needs to be manipulated with x to be the subject. In other words, e to the power of y equals to x. So change from logarithm form to exponential form. Okay, in case you have forgotten how we do that, okay, your ln x is having a base e. Okay, it's like a base e over here. So it's always base to the power of this. So this will be the power. This one base. And then it goes to x. So it's a change of ln form to exponential form. Okay, the logarithmic form to indices form. Okay, this one is covered last year. So x equals to e to the power y. So to find out what is this region, let's just call it Q. That will be to integrate from 0 to ln 2. Okay, and the function that we will have is e to the power of y with respect to y. Okay, because we're going towards the y-axis, so it's always with respect to y. So our function must be in terms of y. Okay, and we know how to integrate e to the power of y. That is just e to the power y. Okay, 0 to ln 2. And then simplifies to e to the power ln 2 minus e to the power 0. E to the power ln 2 is just 2. You can use a calculator to do that. Okay, then e to the power 0, not forgetting that it is equals to 1, not 0. So that will be 1 unit. Okay, so therefore the area of P will be taking the rectangle minus away Q, and we get that as answer in exact form. Okay, you may give it in truncated in 3SF. Okay, since the question did not specify. So don't expect that the question will specify all the time, okay, to integrate with respect to x-axis or to integrate with respect to y-axis. Right? So sometimes you need to have the realization, okay, what you cannot integrate. So in this case, you cannot integrate. That's why we need to think about a different manner. Okay? Whereas earlier on in try 10, yes, we can do it with respect to x-axis, but it is far more complicated and lengthier and not efficient. That's why we integrate with respect to y-axis. Okay? Okay, so we will end our lesson here today. Okay. Tomorrow for home-based learning, covering chapter 17.3. Okay. Then, in that lesson itself, I want to assign homework, you see. So I want to close up, finish chapter 17 entirely before June holidays. Okay, but I don't think it is feasible. They ask you to submit homework by Friday. Okay, I want to understand how many of you take higher Chinese. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.